Excellent. Hi, everybody. Thank you for joining. I see a couple more people trickling in. And hi to all of you watching on YouTube at home. Thank you for being here. My name is Rajiv Krishnakumar. I am hosting today's talk. Typically, this initiative is led by Akash Kundu, but out for this week. We're very excited to have Juhi Singh with us. So Juhi is a PhD student at the Forschungszentrum Jülich. She also did her master's in the University of Pune. And today she will talk to us about quantum optimal control for quantum technologies. So with that, I'll let you take it away.
Yeah, thank you for the nice introduction. So yeah, I think we can get started with this paper. So as you mentioned, I'm doing my PhD here in Forschungszentrum, which is in West Germany. So I work in the field of optimal control. So it's a field inside quantum computing, a subfield you can say, and it's like a theoretical field. And then let's see what we have here. So today's plan would be to discuss really from the basics. So from hearing the introduction, I can assume people already have the knowledge of quantum computing, but I will still go from the really basic things, and then we can know, okay, what are the challenges here and where this quantum control things comes in the picture. And I will show you some examples from my own work, what we did there using quantum control. So yeah, let's see. So first of all, what is quantum technology? We hear a lot about, okay, this quantum computing, quantum simulation, okay, but what is that? So it's just really anything that you can do with this microscopic systems, for example, the atoms, the photons, electrons. So these things that follow your laws of quantum physics. And when you talk about quantum physics, what is that? Probably we know how our classical world works. So how is different? So for example, in classical world, you can really be certain about if you are talking about an object, where is that? You can say with certainty about its position and its dynamic. But in quantum world, you don't have a certainty. Instead, you talk about the probabilities of the dynamic. And you also have the similar thing as Newton's law, which is our famous Rogers equation, where you can give the wave function evaluation, and there are other formulations as well. For example, in classical physics, you have this Lagrangian mechanics, Hamiltonian, and similarly in quantum, you have path integral formulation. And for sure, I'm not going to go into these topics in detail because it will be like the end of world. But yeah, but when you talk about quantum properties, there are really two main important properties that matter when in quantum computing. So the first thing is quantum superposition. And I think everyone knows, but still it's when you talk about classical computing, we just have either zeros or one in our registers. But when you talk about a qubit, it's you can stay in two states at the same time with certain probabilities. So this is a really nice picture stolen from the internet, which shows you how this Schrodinger's cat thing works. So it can be dead and alive at the same time. And the moment when you do the measurement, so the moment you open the box, you get to realize, okay, if it's either dead or alive. But before that, you are with equal probabilities. So this is a really interesting property that you don't get to see in classical physics. But how it helps in quantum computing. So for example, you can see if you have a function and that you want to calculate the value of that function for a given input. For classical, you can give one single input, probably 0 or 1, and then you get an output. Instead, for a quantum, if you have a quantum computation here, you can give two bases or two inputs in superposition, and you can calculate the cumulative output of that input state. And that is something gives you called quantum parallelism. and it gives you the power of doing quantum simulation. So it increases your memory exponentially, which is really necessary if you want to solve like the complex problems which requires large memory, and it will take like years if you want to solve it on a classical computer. So quantum superposition instead is like magic for today, I would say. And the next important thing is quantum entanglement. So what's that is like, if you have two qubits, and if they are entangled, you can take them million years apart. And if you still do something on one qubit, the other qubit will also get affected. And for example, if you see the states here, so if one qubit is in 0, and if after measurement, then you can already say what is the state of the other qubit. And that's quantum entanglement. So like two qubits are always related to each other. And this thing is really used in quantum cryptography because you want to have shared keys within two people. And if you have like a quantum key, then it's really, really difficult to hack that or decode that because those are entangled. And also in quantum teleportation, which we know, I mean, you can just transfer classical information through quantum channels, and it's just so interesting. I mean, these are like the details that people do when they study quantum computing in their bachelor's or master's, but these are, I think, the basics that everyone should know if they want to do quantum computing. But this is just like a motivation from here. And now if you go into the experiments or the real companies or quantum world that is around, is people are trying to build quantum computing from different sort of devices. So it's like not a single platform. So we all know what superconducting qubit, which is like the big IBM thing. And then this neutral atom is also really emerging these days. I'm working on neutral atoms, so I can say it's a nice competition now for superconducting qubits. Then we have trapped ions, which is also kind of similar to neutral atoms. Then we have photonics, and we center semiconductors. These three, I have no idea how they work really, but yeah, I mean, I know that these are also like emerging fields now. So it's really interesting that, I mean, you still cannot say which one will be the final one. Everyone has their own perks. Everyone has their own pros and cons. So for example, in case of neutral atoms, you can go like really large number of qubits. And that's the biggest benefit neutral atom gives you. And also the stability of neutral atoms, because the decoherence is still lower. But the efficiency is better in superconducting qubits, at least what the experiments we are seeing now. So everyone has their own pros and cons. And
sorry, just a quick question if I may. So when you say the efficiency, what do you mean by that?
So efficiency is like single qubit or two qubit gate efficiency. It's still better in superconducting qubits than, because for performing the neutral atoms, you need a set of lasers. I will explain probably something later. Okay. And that is still a bit more noisy than compared to the superconducting qubits.
I see. Thank you.
Yeah. So, I mean, irrespective of what platform you're using, what you want to do in your quantum process, the general description, we can say it like this with this block diagram. You have some input, you want to do some quantum process. For example, you want to create some entanglement, and then you have your target output. So this is your whole quantum experiment here. And you can say either your quantum process is a closed system or an open system. Depends if it is interacting with the environment or not. And both systems have their own constraints or own problems that it is not allowing for 100% efficiency of the gates or of the algorithms that you want to perform. For example, in closed system, even though your system is isolated, the system itself has some constraints. For example, if you take like an optical device, it's not just one laser. It's like a set of laser that passes through a set of optical and electronic devices. So every device has its own constraints. And when the laser reaches the atom, it's not always the same laser. I will show you in the next slides. It's not always the same that you are expecting, even though it's completely closed. So that's one problem there. And then there are some times that these are like really leakage to higher state is a big problem now. So for example, if you want to do something in superconducting qubits or also in atoms, when you apply some electromagnetic field, you always want your states to be in a certain level, if you probably in some excited state or the ground state. But this excitation to other level is always a problem. And these things are affecting the quantum process that you want to do. And in case of open system, the biggest problem is dissipation. So it's like, and dissipation and also decoherence, it's like interacting with your environment. And then you lose information. And this noise could be either Markovian and non-Markovian, and there's like a whole theory behind it. But the whole summary is, if you have this kind of problem, then you don't get a perfect quantum process. Then what our goal is perform these quantum processes in the best way possible, keeping in mind all these problems. And now, so now here comes your quantum optimal control. So what is really quantum optimal control? It's just a set of methods, be it theoretical, so be it analytical or numerical. It's just a set of methods which you can use to shape this electromagnetic fields and to manipulate your quantum dynamics. For example, you are running this quantum process. It is more or less always run by some electromagnetic field. For example, lasers in case of neutral atoms. And then what you want to do is you want to shape those lasers, their amplitudes or their phase in a way that you can minimize the errors. If for the closed system or for the open system, depending on what your error is, you want to minimize that. And then, first of all, we need to ask, whenever we start anything about quantum optimal control, we are asked this ourselves, we discuss with experimental people, is the system really controllable? I mean, there are things that you cannot control. For example, decoherence is something that you cannot completely control. Or if there is a permanent noise in your open system. So for example, if your system is going to a completely mixed state, this is something which is non-controllable. So first thing you need to discuss if you can control the things. So if there are some lasers that you can control to reach your target output or not. And if the answer is yes, then you ask what is the best way to reach your control objective. So what is control objective is like, you want to reach a certain target output. So what will be the best way? And the best way should be something which kind of minimizes your time. So for example, time of performing the gate, and also maximizes the efficiency. So it's just not like you perform a gate in a really small time, but then efficiency is really bad. So it should be a balance between those. So this field, it was like more developed, I would say in 80s, I think, but now it's becoming more of an integral part of any experiments. So we call ourselves engineers, not just theorists, because we work closely with experimental people. We have to know all the nitty-gritty details of the experiments because we want to correct everything that is happening, or at least we want to correct everything that is possible to correct. So that's why this field is like a combination of maths, engineering, and physics. So we use a lot of linear algebra, we use a lot of Hamiltonian equations from physics, and then of course engineering is there. And so next thing is, so what will be the goal for a typical optimal control problem? So usually the quantum process that you do is applying certain gates or doing some state preparation. For example, you want to prepare some particular initial state for your algorithm, or you want to perform certain quantum algorithm. You want to do system identification. Identification means you don't exactly know what your system is or you don't know exactly what your system problems are, and you want to calibrate or at least identify the problems. So these are the main goals for the optimal control theory. And shown in blue, like the state preparation and system identification, I will kind of try to explain these two things today because I worked like for last 2 years on these problems. And then this optimal control technique, as I said, is like analytic also and numerical. Depending on what your problem is, you can either solve it analytically completely, which is not always possible because for that your system size should be really small. If you go to a bigger system size, then you cannot solve it analytically. Then you can go to the numerical approach. And that I would kind of say that you can divide your numerical approach into two different categories. So for example, let's see this one. You have your quantum device, and then you want to correct the error, or you want to maximize the efficiency of your gate or whatever the process you want to do. Then you take another classical simulator. So you write your system Hamiltonian, you simulate your system on a classical simulator, you get the error. So you get like from the simulations, you get what kind of efficiency you can expect in the experiment. And then you try to minimize this error with an optimizer. The optimizer will give you a certain set of control pulses. And after some iterations, it's like a machine learning thing. So after some iteration, you have your optimized control that now you can run your quantum device. So for this open loop or gradient-based thing to work, you should have a proper theoretical model, because you are running this quantum model on your classical simulator. So if your model itself is not correct, then of course it will not give you the correct results. So when you run those pulses directly in the experiment, it will be completely different because the model is different. And then it also relies on the gradient, because for this classical optimizer to work, so I will explain the algorithm in the later slides, but in the optimizer, you need the gradient of your error. So if you don't know the gradient and if you don't somehow calculate it, then it's not possible. It's really based on the gradient. But the good thing about this open loop thing is it's easily adaptable to any of the experimental constraints. For example, if you have like 5 different devices in your experiment, then you can model each of the devices, or you can combine all of them in your model, and then that will be really adaptable. But instead, in closed loop, this is not possible. What we do in closed loop is we just take our quantum device directly, be it superconducting qubit or neutral atoms, whatever you run your quantum gate or quantum algorithm, it will give you some error. And then you use the same classical optimizer, it will give you the controls, and that controls you, instead of testing it on this classical simulator, you directly test on the quantum device. So there is no middle agent in between. So every time you are getting the error from the actual quantum device. So it's nice because then you don't have the issue of writing the Hamiltonian, or you don't have to know the exact model of the system. But then one problem with this, it will be really slow. And doing measurements or doing algorithms on a quantum device, it's also really expensive. So if you want to do this on an iteration, probably you have to perform the same experiment 100 or 1,000 times. And that would be expensive and time-taking. And then you can also not model your system. I mean, for sure, you will not know the model, and you will not know exactly what is happening inside those devices, or what is really distorting or changing your controls. So it will be like a black box as shown here for you. You don't know anything about it. So both methods are used really widely now, depending on what your problem is. If you can write the Hamiltonian, then you can use this open loop, or if you cannot write the Hamiltonian, you can use closed loop. But one small example I can give is like, in case of neutral atoms, we try to use open loop because writing the Hamiltonian there is easy. I mean, it's well-defined system. But superconducting qubits sometimes is not well-defined. There are some non-linearities in the system, which is really hard to model. And there people usually try to do the closed loop thing. And then with this, we know, yeah.
Sorry, I just had another question on the previous slide. So then are there, would there be any benefits to doing a combination? So something like where you model your Hamiltonian, it's not quite exact, but it's good enough. And then you mentioned that the open loop is faster. So you do that, and then occasionally, time to time, you use like a closed loop one for kind of tweaking the...
Yeah, I mean, that's a good observation. Actually, people are doing hybrid approaches also. So they first do, as you said, they first do this kind of open loop, and then they have some better pulses, which is not completely out of range. So now at least they have something in the ballpark, and now they can do fewer experiments and correct it more better. So this is the hybrid approach is still being used.
Thank you.
Yeah, thank you. So now we know how quantum optimal control works. So first we want to know what is our target quantum process. So what we want to do we want to do any state transfer? Do we want to do any quantum gate or run any algorithm? And then we ask the experimentalist, what are your control variables, what you can control? And then what is your system constraints? So for example, one of the examples with system constraints will be the lasers cannot have an arbitrary amplitude. I mean, in the devices have some frequency range. You cannot go beyond that, or you cannot really make the lasers move fast too much. Like they have like certain rise times. So these are like the system constraint that you have to follow in your simulations. And then you write your control objective. So for example, for the state transfer or for the gate, you have like a target unitary gate, maybe entangling gate. And then you do your simulations, you reach after the total time, you reach a certain gate. And then you calculate the overlap between your target gate and the gate that you have reached. So this will be your control objective. And that is something that you want to either maximize or minimize depending on how you want to write. And now you have your control objective, or also called the cost function. Now you ask yourself, what is the method that I want to use? Do I want to use this open loop thing or closed loop thing? And depending on that, which algorithm? So it's like the whole process of quantum optimal control runs like this. And okay, yeah. So if there's any question till now, otherwise I will go to a specific example, because now we know how quantum optimal control work, but maybe learning with an example is much better. So if there is no questions. Okay. So as I said, I currently, or at least I was working with neutral atoms, specifically Rydberg atoms. So this is one of the platform which is leading now. So there's like fewer companies and also big research groups which are working with Rydberg atoms. But what is really Rydberg atom? So it's like atoms which have high principal quantum numbers. So what does it mean? So it's like one of its electrons is, so the atom is excited to a really high N. And then it gives you a large interaction strength when you are at really high N. And that for doing that, what you use is you use a set of lasers to excite your atoms. I mean, I will show you later how this excitation is helping for performing gates. But the best thing about this thing is when you excite the atom, it gives you a long-lived state, which is really important when you want to do any quantum process. If your states are not long-lived, then it suffers from decoherence. And it has like a larger time, so you can also perform gates for a larger duration, which gives it more stability. And since these are like just atoms, you can arrange hundreds of atoms in 2D or 1D structure, and then each atom represents a qubit. So now you also can go larger qubit size, which is nowadays the biggest benefit of using neutral atoms. People are just using a set of laser, creating optical lattices, and they have like 100 qubits now. It's just that the phase problem and also like balancing the qubits or the atoms, if they can do it, I think it can perform really well. So with this little motivation, let's see how this Rydberg atom gate works. I mean, first of all, I would like to say this, optics people like to use a different notations than we usually use in quantum computing. For them, 0 is the control and 0 is like you do control when you are in the 0 state, something like this. But the basic idea is you want to implement a control phase gate, for example. Then you take two atoms, you have two, the 0 and 1 level is like the hyperfine structures of hyperfine levels of your atom. And then you take a Rydberg level, which is like a really large N with a really large energy gap. And then you apply a laser and couple your first level to your Rydberg state. And that kind of gives you a phase shift. So depending on which level you excite, if you excite this first qubit, then automatically the second qubit is not able to go to the Rydberg state. That is called like the Rydberg blockade. Because of this large interaction energy, for the second atom, this Rydberg state energy gets shifted. So now this transition is not allowed. So in the end, after using these 3 pulses, so first a pi pulse, then like a 2 pi pulse on the second atom, and then again a pi pulse on the first atom. So eventually you will get a phase shift of, I think, -1. So you can apply now. It's like a control gate now. So and this is the control atom, because this is the controlling the whole process. If it gets to the Rydberg state, then this is not able to do it. So the second atom is controlled by the first one. And these are like some different protocols that you can use for doing this control phase gate. And we know that if we can do control phase gate and we apply pi by 2 pulses to the control phase gate, then it becomes a control knot. And if you have a control knot, then you can build like any gates from it using single qubit rotations. So now these universal gate implementation is possible with Rydberg atoms. So the basic idea behind then is this excitation. And here comes the optimal control part. Because exciting this from the ground state to the Rydberg state, they need laser. And doing this is not perfect, because now it's a system which also suffers from dissipations. It has a lot of constraints. And yeah. So for example, here, as I said, if you want to go from the ground state, from the Rydberg state, you need 2 set of lasers. You can also do it with 1. So ideally, people used to do with 1, they directly just apply 1 laser and just go directly from ground to the Rydberg state. But that needs, because the Rydberg state is a really high energy state that requires a laser with high intensity. And that means high intensity laser means more noise, and also more power. And that is something that the experimental people don't want. So they came up with the idea of why don't we use 2 lasers instead of using 1. So we just apply 1 laser from ground to some intermediate state, and then another laser from intermediate state to the Rydberg state. So this 2 photon process, it's called a stir-up process, which is like really helpful for this Rydberg excitation. And for this is, so now we are in a sub part of the Rydberg domain. We want to do gate, but for that, we want to do the Rydberg excitation. So this is so our quantum process is now this single atom excitation. And this is a Hamiltonian of that single atom excitation. I don't think so going into the details will matter, but I will just explain what is the physics or what are at least these things means. So for example, this omega B and omega R terms are the laser or the Rabi frequencies that you want to do from the ground state to the intermediate and the intermediate to the Rydberg state. And these are the detunings from this. So the laser detunings that you have at these two levels. And then you use this Lindblad term here. So this whole term here represents the all sort of dissipation that is happening in the system. For example, one of the possible process is the moment you go to this intermediate state, there is a probability that the atom will spontaneously emit to one of the other ground state. By the time you're applying this laser, there is a certain probability that it will go to the other ground state. And this is something that we want to minimize. We don't want this to happen. We don't want to lose the atom population from here. And the other possibility is this losing the atom from the Rydberg state also. So this losing atom, the spontaneous emissions are represented here in terms of your Lindblad. So this is something we cannot control, but there is this set of lasers that we can control to minimize these things here. So we are not controlling the effects. Instead, we are controlling the laser so that we can minimize these things. And then if you now compare this equation with the earlier equation that I showed you about, then you can see this comparison that this H0 is the part which we cannot control. We call it in control language, we call it as the drift Hamiltonian. So something that you cannot control, it is the driving Hamiltonian of your system. And then this is the part which is controllable, with this UJK being your controls. So now your HJ here is these two parts, this PR and GP part, and then UJK are the controls. So this omega B and omega R, the Rabi frequencies are something that we are trying to control here. And our target is now to reach Rydberg state. So our target state is R here. Then how you can write your control objective is you know your target state, you will do your simulation, you will get a state, some state after total time t, some x, then you take the overlap and you see how much efficient your process was. So you will get a probability and you can check if it's 1, then it was a perfect process. And if it's less than 1, then you are not perfect. And we want to maximize our overlap, or in other way, we want to minimize this cost function. So now on the same workflow we saw earlier, we wanted a quantum process. We have it. It's Rydberg atom excitation. We have our control variables. This is omega B and omega R. We know our system constraints in form of equation, which were the dissipation effects. These are there and we have to deal with it. And we also have our control objectives. And now it comes to control method. So the particular control method that I used in my work was GRAPE. So it is a part of the open loop control. So we are here doing open loop control, the gradient based thing. So I will just try to explain what GRAPE is next. So if it's like no questions, then. So GRAPE is just a gradient-based method, as I said, open loop control. So I think many of the people already know what gradient descent means. It's like going around some surface and just finding a minimum value there of a function. So for that, you always follow the path of the gradient. So you can do either gradient descent or gradient ascent. So you can either go in the direction of gradient or opposite to that. These are the basic optimization things that people also do in classical world to do optimizing classical problems. It's not something that is just done in quantum problems. So but doing it for our case, what we have to do here, we have our pulses omega B and omega R. And then we cannot solve this system analytically. So what we do is we first discretize our pulses in small time steps. And then we have, for example, we have the total time t, and then we can write our Hamiltonian in this form, which I already showed. And then each unitary operation at each time step will be the exponential of IHT minus IHT. So it's like the unitary operation, the usual unitary operation we write. And then the total unitary operation or the total state transfer, you can write as the product of each time step. And then in that case, your cost function would come out as the trace of your target and the state that you reached at time t. And then you can write your final cost function as 1 minus this overlap. So this is how the basic grade thing works. And now you just take the gradient of your cost function and you go opposite direction to that. So every iteration you update your control u and you go till the point then your gradient value is really, really small. And at that point, you stop your iteration and you reach your maximum or minimum cost function, depending on how you define it. And these are the optimal controls that you have. So this will be like a piecewise constant. So for example, in this dt time, your u value or your control value will be fixed. And so is your unitary operation will be fixed at that point. So this makes your Hamiltonian time dependent. So for each time step, your Hamiltonian has a different value. And this is not mentioned in the slide, but there's an interesting discussion always that we have is like, usually when you say that you change your Hamiltonian, you also change the eigenstates. Because you have a certain Hamiltonian, for example, take a matrix, and if you change the matrix, you diagonalize it, you get a different eigenstates. And that is something that requires us to do this process in really small dt values. Because if your dt is large, then you are drastically changing your Hamiltonian. And that is something that doesn't matches with the real system. This discretization has to be really, really small. So we always try to keep a balance, but making the discretization small also makes your optimization really slow, because now you have to optimize 1,000 time steps probably, or to 10,000 time steps. So we always have to find a sort point or critical point where we are still realistic, but then we don't want our optimization to run for months, for example. And then I explained you in basic what the method I will be using or I have done it. And then we come back to our Rydberg system experiment. So as I told you, so first of all, really sorry for this DZ diagrams, really bad at that, but we want to do the Rydberg atom excitation. And as I told you, we have it's not just one laser which is directly going to the atom. It's a set of devices that work in between. And for example, you did your optimization, you have certain pulse at this point, and then you send it to the computers. It gives you some RF frequency. So it's just oscillate your pulses. And then you have this oscillating RF frequency. And then that passes with this AWG, which is arbitrary waveform generator. So these are just some electric devices which is just passing the pulses in a certain form that the experiment can accept it. And then this AWG passes it through this AOM, which is acoustic optic modulator. So this thing is able to modulate the pulse amplitudes and is able to change the phase. So this is the thing that experimentalists use to change the pulses as they want. And then it finally reaches to the atom. So it finally reaches to the atom and then it does the process of excitation. And you can also place a photodiode in between to measure your pulses. Oops. So, and what you do now is Now you have the pulses, which is doing the excitation. And then, so our work was optimizing this particular set of pulses. And the results that you can see on the right was really interesting, because as we are optimizing our pulses, we saw that there was a set of lasers for that we were not able to optimize it because it has a lot of noise in it, this old set of lasers. And then we talked with the experimental people and we came up with the idea, and they bought some new set of lasers. And then you can see here, even for smaller time steps, you can reach a really good efficiency. So for example, every point denotes your total time. So your total time for the Rydberg excitation. So, and this is like 0.9 microsecond. So for that means like in 0.9 microsecond, you can go from the ground state to the Rydberg state. But with optimal control, we came up with pulses that were able to do the same thing in 0.3 microsecond. So that was really remarkable, because they wanted to do this excitation in the least possible time. Of course, because of decoherence, you don't want to run any quantum process for longer times. And these were the kind of pulses that we saw. As you can see, it's like a piecewise constant for every dt. And now you can think, okay, now we have the optimal control pulses, we can do the experiment, we have the nice efficiency. So it's a done process, but instead it was not. We still had a lot of problems after that. It was like it's like really a story. So when we have our pulses, we gave it to the experimental people. So we did all the simulation, we optimized it in our classical simulators, and then it was like time to do it in real experiments. So this was the RF frequency that we used, and we noticed that after passing through this AOM, it was not the same pulse that we were reaching. So you can even see here the standard deviation of this Gaussian here is much larger than the standard deviation of this Gaussian here. So the pulses were getting distorted. And a particular omega B and omega R, so particular control gives you a particular excitation efficiency. And if there is a change in your controls, that means then there is a change in your excitation also. And this is something that we didn't want it. And we also test the data, a different set of data, like we test hundreds of data, and we realized that this change was not something that we could ignore. So for example, you see it's like this green curve was something that we were sending, and this blue was something that we were noticing after this theorem. So it was something that we should not ignore. And then we decided, okay, we need to optimize these things also. So here comes like the another use of optimal control, system identification and calibration, the thing that I said, like this is the other thing I want to explain. So since you don't know what is exactly happening inside this AOM that is causing this thing, we wanted to calibrate it somehow. And for that, the first thing engineering mind works is it's an electronic device. It should have a response function. Let's just measure the function and correct it. And for doing this response function, usually people calculate the transfer functions of any device. So what you do is you just take your input pulse, you pass it through your systems, you get output pulse, and you just do the Fourier transform. And you measure it, and then you can do the reverse transformation. So you can just correct your pulses accordingly. So this was a straightforward thing to try. And we did it on our pulse, and instead the results were really bad. So we kind of like, okay, what is happening here? So this was like our initial pulses. The red ones and the blue ones were something we wanted to reach after the passing through the device. And the transfer function was giving us something which was like in green. So some of the cases where it was still fine, but mostly it was failing. So, and then we started wondering, okay, what is the problem? I mean, why this simple calibration, it's not working? And then after a lot of thinking, a lot of research, we kind of realized that these AOMs are not really linear devices, because these have optical effects, and optics is mostly nonlinear. So doing a linear transfer function would be not the best thing to do. And then we decided, okay, let's have some general optimization scheme that we can include in our optimal control to measure some nonlinearity. And this is currently one of the biggest problem in every quantum system, is having some kind of nonlinearity. Sometimes you can measure it, sometimes you don't even know where it's coming from. So we decided to have like some general scheme to do this. And now I won't go into the details because it's just beyond the whole motivation of quantum optimal control, but just to give an idea what the nonlinearity can do to your system or any kind of distortion. So here it's we applied some sort of simulated distortions in our control pulses, and we noticed that how bad our excitation error were getting every time we were applying more and more nonlinearity. For example, for this distortion C in the green, we applied a high nonlinearity in the system, and our excitation error went to like 0.5, which is like 50%. So it's not even something that we want to do at some point. Before this distortion, this blue curve was here. So it was like without any distortion, the ideal thing that we would have expected with optimal control. But it lost all its value just because of this distortion. And these were like just different experiments that I did as my work in my last 1-2 years. And then we came up with this complex, scary equations. I mean, being a theoretical physicist, I think I should write some scary equations on the slides. So this is, it looks scary, but it is kind of just the generalization of the linear response theory I showed earlier. So when you calculate the linear transfer function, you do the Fourier transform, but Fourier transform is something in frequency domain. And it's the same, it's like the same in time domain is convolution. So you do convolution in time domain and you do multiplication in Fourier domain, but both are the same things. And for going to the higher orders or nonlinearity, you do the same convolution, but now with x square terms or also x cube terms, depending on how much complex you want to get. So if you stop at this point, then you are just this linear transfer function. But we extended the model and we went to higher orders. And we tested it on our data, and these blue things were some kind of distortions, nonlinear distortions. And with this model, we were able to estimate it with a really high order efficiency. So the estimation error was like around 10 to the power minus 8. And it's like, okay, it's great. Now it can work. And this was like a remarkable thing because earlier, nonlinear transfer function is not something new. People are doing it. But what was new was doing it in quantum control and in quantum technologies, because quantum systems are already so complicated. At least the experimental people, I can assure, they want to just ignore these small things. It's like, no, don't want to deal with these things. If it's causing like just 5 or 10% efficiency, then fine, we will ignore. But it's something that as an optimal control theorist, we cannot. It's not possible to ignore, because these efficiencies are something that we are trying to optimize. And for us, losing these things was a major problem. So then we came up with this idea, and now, okay, yeah, this is, I think, the last thing. So now you have your method. You estimated, okay, now this is the problem. Now I have my transfer function, which is linear or non-linear, whatever. Now how I can include it in my optimal control, because I don't want to do it manually. It should be something that is done automatically during the optimization. So as I showed you, when you update your control at every iteration, you take the gradient of the cost function and you just go in the opposite direction of the gradient. So now just to include the transfer function, the extra thing we had to do is this, in taking this gradient, we have to do taking two different gradients. So the gradient of the new pulse with the old pulse, and then the gradient of the control with respect to the new pulse. So it's just a product rule. Ideally, it would have been just this thing, but now our pulses are changing, so we have to take the gradient with respect to the new pulses also. And where this gradient was just our transfer function. So it's this Jacobian that you can calculate. And then we use this new gradient into our optimization, and we were able to do the corrected. So you can see like the corrected efficiency is in mostly matching with the ideal one that we were expecting. So we were able to handle the distortion really well. And so this was like the work which I did in my last 2 years. And it is a part of optimal control theory that is really important, system calibration. For doing any quantum process, you need to have this model. You could also do it without using this open loop thing. As I said, if you didn't know what your AOM was doing, you could have just applied this closed loop thing. Don't care about whatever is happening, get an error, get the feedback, do it again. But in that case, if you want to change really small things, you're not able to do it because now it becomes a black box. You can't control and you can't know the things which is happening inside that. And so with this, I would come to my conclusion. So what we saw so far, or at least I tried to explain, was what are the quantum processes that we are doing, the fundamentals, what are the challenges that we are facing currently, and how we are, from optimal control, we are trying to solve these problems. So this QOCT, or like quantum optimal control, has becoming a really big thing, a part. Everyone wants to include this to a better efficiency. And recently, even some of my colleagues are also using different branches of machine learning, like reinforcement learning, to do better quantum optimal control. Because when you go to really large system sizes, you need some sort of reinforcement learning or even neural networks to do the simulations. So we are trying from every direction to come up with better pulses, better experiments, and hopefully we'll reach someday. Okay, with that, thank you so much. If you have any questions.
Awesome. Thank you so much. I really appreciate the talk. It's yeah, I think a lot of people in the field, especially those that aren't experimentalists, will just be like, I just need a controlled phase gate. Like, that's fine. But clearly there's a lot of work. I mean, this shows that not only there's a lot of work that needs to go behind such a simple statement, but also there's some really, really interesting physics. So thank you for bringing all that to the forefront. Are there any questions from other people in the audience today?
I have one question. So like you mentioned about this platform for the atom. So what do you say your personal understanding, in the sense like many people have the different views about different things, but about in context of the platform, which platform you think has the more advantage as of now?
Yeah, I mean, I think every experimentalist get to ask this question in every conferences, and they always try to get rid of the question instead of answering it. But I think personally, so it's really I think for me, it will depend on what problem you want to solve. People will use a certain device. So if you want something to do a really high efficiency, I mean, then you go to superconducting qubit. It's not like neutral atom also reaching now 99% or something, but it's still lower than superconducting qubits. But if you want to do some experiment which requires you to do large number of atoms, for example, the biggest use of neutral atoms now is quantum simulators. Even like more than quantum computing, people are using neutral atoms to do quantum simulations, because for that you need larger number of qubits. And there you can easily use, like there's a company called Pascal, and they're now selling their quantum simulators and it's working nice. So it depends on what problem you want to do.
Okay, so it may be that some devices are good for some problems. So yeah, depend on application, there would be a diversification of different platforms. Okay, and you are like so Jülich is involved in superconducting as much as I know, but there are also other platforms where also Forschungszentrum Jülich is involved.
So yes, Forschungszentrum Jülich has experiments which are on superconducting qubit, but now they have also brought this machine from this company Pascal, so they are also building up a new experiment with neutral atoms too. But the research, the basic research, we also have groups who work on semiconductors too.
Okay, yeah, okay, good to know.
Yeah.
Any other questions? Okay, let me read this out loud for the people at home. But Kati says, very well delivered, Juhi. I have a question about the correction function in the previous slide. How expensive is the error correcting step and how well does it dampen over time?
Yeah, I mean, so the error correction that we did is if you know your exact transfer function, then calculating gradient is not a problem. I mean, we also derived a particular analytical formula for the gradient too that I didn't show in the slide, but it's in the paper. So, and if you know the analytical formula, then calculating gradient is really fast. It becomes a problem when you don't know the exact function. Then the optimization uses this finite difference method to calculate the gradient, which is usually slow. But I mean, I think it didn't really matter when we used the transfer function in the optimization. It was equally speed as maybe a little bit longer, but it didn't make a large difference at all.
Okay, maybe I'll ask a question. Sorry, Kati says, thanks, it makes a lot of sense, Juhi. So maybe going from piggybacking off the previous question about different platforms, just focusing on neutral atoms, which atoms were you focused on, and do you have any opinions on which specific atoms are interesting?
So right now I'm working with lithium atoms, and earlier it was potassium, so I changed the experimental groups that we were working with. So, but as long as any alkaline matters like that you can excite to higher N, it works as a Rydberg atoms. And with neutral atom, it is not only this protocol that works for. So this Rydberg atom is like the excitation thing, but you can also do gates without excitation. So for that, the current project that I'm working on, I mean, I cannot go like too much details, I'm not allowed to, but it's just that the thing that you can do is you have your optical lattices, you have atoms, for example, a 2D structure like an egg tray. So each atoms are inside one lattice. And then what you can do is you can do collision between two atoms. So you can lower your barrier, and then it's like quantum tunneling. So for example, you want to do a swap gate. So your one atom has one spin, another atom has a different spin, and now you want to exchange their spins. That is like a swap gate. Then you can just lower your barrier and allow the atoms to tunnel to the other well. And that is something that's really interesting because it doesn't need extra set of lasers to excite it to the Rydberg atom. It's like a completely different protocol, but it's still neutral atoms. And there what we do as a optimal control is we control how fast or with how much magnitude or what should be the best way to change this barrier strength. So we can do this swap in the least possible time. So, I mean, neutral atom is like it's like a set of atoms, but it has like different protocols of performing the gates.
That's super interesting. And so this method of having some control over just like making a swap gate by lowering the potential. So this has, and there's no Rydberg atoms involved in this this method?
Yeah, no, so there's no higher excitations here. Atoms always stayed like in their ground state.
Okay, so do you, I mean, I guess if you're able to answer and if you're allowed to, do you know what the advantages and disadvantages of a method like this is compared to the Rydberg atoms?
So, for example, the advantage would be, as I said, like in case of also Rydberg atoms, you need this optical lattices. So you already have this one set of lasers.
Mhm.
And then for the excitation, you need another set of lasers. And the more laser you add, the more noise you get, the more decoherence you get. So its first thing is getting rid of these things. And the second thing is, even if the Rydberg atom has really high lifetime, so when you excite an atom, it stays at the Rydberg state for a larger time. So it gives you large enough time to do your quantum process, but it still kind of spontaneously emit at some point. So this is something that is not in case of when you don't even excite it, when you just do the gate by collision. You don't have this lifetime issue there.
Because what is the lifetime of a atom in a Rydberg state, roughly?
So it's around, I think, 100 microseconds.
Okay, that's still seems fairly long.
Yeah, I mean,
right?
yeah, that's still fairly large enough for performing any gates.
But then yes, you still always have some chance of it decaying.
Yeah.
And maybe my final question is: so when you have your theoretical models and then how to change your pulse, I guess. The way it's implemented is through, in that diagram you showed, it's through that arbitrary wave generator. Is that how the implementation gets done physically?
Yeah, so we give our pulses in some format, some file, and then you pass it through the arbitrary waveform generator, and it generates this RF frequency. So it's oscillate this nice Gaussian with a cosine pulse. And now you have your RF frequency, and this RF frequency drives your AOM. And then you get a final Gaussian pulse shape that is applied on the atom.
And so you do that, and you put this fairly complicated shape, and then out the AOM pops this fairly nice beam.
Yes. So this is the thing that these are the system constraints that we have to keep in mind when we do the optimization. For example, the AOMs have a certain rise time, as we mentioned. So if you give a pulse which goes from here to here like in no time, or is like crazily changing, then the AOM will try to smooth it out because it's out of its own frequency range. So in the optimization, we make sure that we always follow this system constraint and yet come up with a pulse which follows the constraint and gives the maximum efficiency possible.
That's really amazing. Yeah. As a former experimentalist, how that makes a huge difference to have somebody to be like, by the way, if you do this, your pulses are way nicer.
Yeah, I mean, we always come up with new ideas. Maybe you should do the experiment like this, maybe like this, because for them, because they want optimal control, is because they also don't know which is the best pulse. I mean, for example, for the thing that I said is this tunneling thing, this thing that I'm currently working is, if we know from quantum tunneling that if even if you don't do anything, like at certain point, you will have this swap. But it's not like you want to wait forever. You want to do in as minimum time as possible. And for that, they don't know how fast they should go. And then they can do it maybe by doing it 2,000 times different trial and error method. But doing it experimentally is just so expensive and not a feasible option. So here we come and we just do the simulation. We do it 100 times, but in a computer, not on a real device. And then we give them a pulse, okay, and now you can try it. So for them, it's just doing the experiment once. So it eases them a lot.
Sure. Any other questions?
Yeah, I have a question. Like, I'm also from experimental background, so in that side, so you mentioned about some of the sub challenges, in the sense you mentioned about the AOMs, that there will be something nonlinear many times. So in general, like, as you are sure about this whole setup as you are working with experimentalists, what are the challenge in the sense, do we need maybe a tunable lasers, or like there are some experimental capabilities that we are still lacking that we will need to realize more or for better performance or better productivity?
Yeah, I mean, there are a lot of still difficulties in the experiments where, I mean, the experimentalist always wants to buy the best laser available in the world, and they're still not able to do it and the laser companies are trying to make the best lasers with the least possible phase noise, or which like now there is this femtosecond thing, so people are trying to do like the smallest possible lasers. I mean, it's just beyond crazy explanation, because the laser and these AOM devices are improving every day. The companies are trying to improve their performances. So as better as these individual devices are, you get better performance. So it's still not at their perfect level. So
Okay.
I mean, I showed like you in the slide. Where's this? Let me go. Yeah. So for one example is when they were using this old lasers. I mean, the experiments was exactly the same. It's just that when they changed their lasers, we could do much better. So it was because this laser had a lot of noise. It was not perfect. And the set of, every laser has a certain wavelength. So this wavelength was not ideal for this particular experiment. So it's like they have to improve their experiments after every 5 years, I would say.
Oh, okay.
Yeah, I mean, for them, it's a really problematic thing, and they want to, because even like buying something is not really like you can do it just by a click of the fingers. You have to really do some analysis, talk with the theorist. Okay, what should we buy? What would be the best thing to do in the experiment? You cannot just something buy and do the trial. Okay, it doesn't work. So
Okay.
this is also where at least some of my colleagues are working to help them to find the best devices possible. We do the simulations and we came up with, okay, maybe the laser with this wavelength would work better for you.
Yeah. And you also mentioned about the pulse shaping, but also about the femtosecond laser. So because that's also the hot topic of research these days, that some startups are doing to have more and more small this femtosecond, or maybe going for even shorter scale. So these are also like very important for this quantum computing.
Yeah, I mean, I would say so. You don't want to go too fast, because then that will be another problem, like excitation. There was a point, the plot that I showed like there was a point when our optimization even couldn't optimize for like really short duration, because at those points, for example, you could either excite your atom out of your optical lattice. If you apply a really short pulse, or if you apply a pulse with really high intensity, then probably the atom is not even there anymore. So you have to always find a soft point. And that's why like a lot of research going on. Okay, what would be the best pulse length, or what would be the best wavelength that we can use?
Okay. Yeah. Yeah, it makes sense. And there is one stupid question maybe that so there is this quantum annealer which is also being developed, or that's from the long time, and now this is where we realize the gate-based quantum computer. So like what are the overlaps in between them, or there are some common challenges in both of them, or maybe just to share your view on this, because I get a lot more confused in both of these, because I'd say University of Hamburg is developing RIMAX. So just want to know your views about this.
Okay. Yeah, I'm not an expert on quantum annealers, but as far as I understand this, I mean, as an optimal control theorist, I care about the experiments on, I mean, making the devices. I'm on the other side of the research making it, but I mean, if people use it as quantum gate-based or annealing, it's like on the other side of the code. How do you use it? It was never like a concern of mine, but as far as I understand, quantum annealing is you can use it for I guess, a particular set of problems, because it depends on what Hamiltonian you want to find the ground state of. So quantum annealer every time tries to, whatever problem you give it to it, it tries to find the ground state energy. So it converts that problem to finding a ground state energy. So quantum annealer is not really a universal quantum computer, as I would say, as far as I understand. Instead, but it's easier to make because then you don't have this gate arrays thing, and it works like a quantum simulation thing. So you just go simulate your Hamiltonian, find the ground state energy. You don't have to apply a lot of gates, because every gate then adds an extra error to your system. So this is like the basic working difference as far as I understand in quantum annealers and quantum computing. Which is more advantage, that I don't think so. I have an idea. I mean, of course, if you can build a universal quantum computer, then that would be more advantage. But that's not possible. I mean, we are still in this NISQ era.
Yeah, makes sense. Thanks.
Thank you so much.
I think on that note, we will end. It's been a little bit more than an hour that we've had this conversation. So again, thank you very much, Juhi. I think if you have just 5 or 10 minutes to stick around, that would be great for a slightly more informal chat.
Yeah, sure.
Thank you for that. And so I'll end the call, the recording now. And so thank you again.